NASA's twin Voyager probes, launched in 1977, amazed the world with their historic journeys to Jupiter, Saturn, Uranus, and Neptune. Both probes continue their voyage into interstellar space 45 years later. Researchers, some of whom are younger than the spacecraft themselves, are currently using Voyager data to unravel mysteries both within and beyond our solar system. In many ways, NASA's twin Voyager spacecraft have evolved into time capsules of their era. They contain around 3 million times less memory than contemporary cell phones, transmit data at a rate about 38,000 times slower than a 5G internet connection, and each has an 8-track tape recorder for data storage. Despite these limitations, the Voyagers are still at the forefront of space exploration. What are they doing right now? What will the Voyager spacecraft encounter next? Let's find out. Two of the most amazing spacecraft ever launched would never have taken flight if the stars hadn't aligned. In this instance, the 4 largest planets in our solar system were the stars. As a result of this rare alignment, a spacecraft could gain speed from the gravitational pull of each large planet it passed, as if being pulled along by an invisible rope. This gravitational assist sent the probes flying on their course. One drawback, though, was that the alignment only occurred once every 176 years. A spaceship would need to be launched by the mid-1970s to reach the planets while the lineup was still in effect. As it turned out, NASA created 2 spacecraft to make the most of that once-in-a-lifetime opportunity. Within 15 days of one another, Voyager 1 and Voyager 2, which were identical in every way, were launched in the summer of 1977. They have been operating in space for almost 45 years, sending data back to Earth every day from the solar system's farthest known planets. They have lasted longer and traveled farther than any other spacecraft in history. According to our best understanding of the dividing line between the Sun's sphere of influence and the rest of the galaxy, the Voyagers have entered interstellar space. They are the first human-made objects to do so and will likely hold this distinction for a few more decades. Overall, it's not a bad record given that the Voyager missions were initially only intended to last a few years. The Voyager spacecraft's early observations of Jupiter's and Saturn's moons stunned researchers 40 years ago. They revealed the presence of active volcanoes and furred ice fields on worlds that astronomers had assumed would be as inactive and cratered as our own moon. Voyager 2 was the first spacecraft to pass by Uranus in 1986, and 3 years later it flew by Neptune. It is the only spacecraft to have traveled in this way so far. Currently, the Voyagers are surprising physicists with unexpected discoveries about the unexplored regions they are venturing into as pioneering interstellar probes more than 12 billion miles from Earth. However, their incredible journey is nearing its end. Over the past 3 years, NASA has turned off heaters and other non-essential components to stretch the spacecraft's energy reserves as far as possible, estimating they could last until 2030. This is a bittersweet moment for the scientists involved in the Voyager project, many of whom have been with the mission from the beginning. They now face the completion of a project that has far exceeded their highest hopes. 546 days after its launch in March 1979, Voyager 1 arrived at Jupiter. Voyager 2, which took a different course, arrived in July of that same year. Both spacecraft were equipped with Vidicon cameras that used red, green, and blue filters to create full-color images. These spacecraft were built to be stable platforms, with their rotational velocity more than 15 times slower than the crawl of a clock's hour hand. This helped minimize visual blur as they traveled through space. Despite still being 3 to 4 months away from Jupiter, the spacecraft began transmitting the first images of the planet. These images delighted standing-room-only crowds at NASA's Jet Propulsion Laboratory, JPL. It was absolutely unexpected when Io, one of Jupiter's moons, showed up in color. Prior to the Voyager missions, it was believed that all moons in the solar system would appear similarly drab and cratered. The incredible diversity of moonscapes that the Voyagers found near Jupiter and Saturn had not been predicted. The first hint that there might be more moon types than astronomers had imagined came when the Voyagers were still about 1 million miles away from Jupiter. One of their instruments, the Low-Energy Charged Particle (LECP) detection system, detected some peculiar signals. Io, as revealed by the Voyager's cameras, had active volcanoes. This small world, slightly larger than Earth's moon, is now understood to be the most volcanically active body in the solar system. The materials ejected by Io's volcanoes give the moon its distinctive hues and the anomalous ions that strike the instruments. Io's greatest volcano, Pele, has produced plumes 30 times higher than Mount Everest, and its ash field is almost the size of France. The Voyager spacecraft captured more than 33,000 images of Jupiter and its satellites. Each photograph revealed something new. For instance, Jupiter has rings, and Europa, one of Jupiter's 53 named moons, has an icy covering that is now thought to be more than 60 miles thick. After leaving Jupiter, the Voyagers received a farewell kick of 35,700 miles per hour thanks to a gravity assist, without which they wouldn't have been able to escape the sun's gravitational pull and continue their journey to the stars. The Voyagers then split off at Saturn. Voyager 1 passed by Titan, Saturn's moon cloaked in orange haze, and then turned northward, away from the plane of the planets. Voyager 2 continued alone to Uranus and Neptune, discovering 10 new moons orbiting Uranus in 1986 and recording the fastest wind speeds ever measured for a planet at Neptune, up to 1,000 miles per hour. Neptune's largest moon, Triton, was found to be one of the coldest locations in the solar system, with a surface temperature of just -391 degrees Fahrenheit, -235 degrees Celsius. Ice volcanoes on Triton eject nitrogen gas and fine particles as high as 5 miles into the moon's thin atmosphere. Had astronomer Carl Sagan not been part of the Voyager 2 mission's imaging team, its pictures of Neptune and its moons might have been the last ever taken by either spacecraft. NASA had planned to turn off the cameras after the grand tour was officially over, as there would be no more photo opportunities once the spacecraft ventured beyond Neptune. Despite the project's extension and renaming to the Voyager interstellar mission, Sagan pleaded with NASA leadership to allow Voyager 1 to take one final set of pictures. As a result, on Valentine's Day 1990, Voyager 1 turned its cameras back toward the inner solar system and captured 60 final images. One of these photos, known as the pale blued, captured Earth from a distance of 3.8 billion miles. This image remains the most distant depiction of our planet ever taken. Today, both Voyagers are so far from Earth that a one-way radio signal, traveling at the speed of light, takes almost 22 hours to reach Voyager 1 and just over 18 hours to catch up with Voyager 2. Every day, they advance by 3 to 4 light seconds. The NASA Deep Space Network, a trio of tracking facilities spread across the globe, is their only connection to Earth. As the Voyagers move farther away, their signals grow fainter, making it more difficult to hear their faint whispers. Despite this, the Voyagers have challenged astronomers' expectations about what they would find in interstellar space. It's important to avoid confusing the solar system's limit with the boundary of interstellar space. The Oort cloud, a distant collection of comet-like bodies held together by the sun's gravity, may extend halfway to the nearest star. It will take the Voyagers at least another 300 years to reach its outer edge. However, interstellar space begins where the solar wind phenomena end. The solar wind is a continuous outpouring of charged particles and magnetic fields emitted by the sun. Moving at hypersonic speeds, the wind blows out from the sun, forming what astronomers call the heliosphere. The heliosphere's expansion is eventually constrained by interstellar matter, creating a boundary with interstellar space. This boundary is preceded by a massive shock front known as the termination shock, and beyond it lies the heliopause, the true border between our solar system and interstellar space. Located in the heliopause, as close as Jupiter, Garnett's calculations from 1993 put the distance at around 25 times farther, between 116 and 177 astronomical units. 1 astronomical unit, AU, or 93 million miles, is the distance between the Earth and the Sun. Garnett's projections from 1993 were accurate before one of the Voyagers ultimately reached the heliopause. About 20 years had elapsed. Voyager 1 had actually detected the anticipated rise in plasma density. Its plasma wave detector had inferred an 80-fold increase. However, there had been no indication of a shift in the ambient magnetic field's direction. Shouldn't that change have been apparent if the vehicle had traveled from a place where the magnetic field originated from the sun to one where it came from other stars? That was a shocker. In November 2018, Voyager 2 arrived at the interstellar seashore but did not notice any magnetic field changes. When the spacecraft reached the heliopause at 122 Australian dollars from Earth, the same distance reached by its twin 6 years earlier, it added yet another riddle. All theoretical models predicted that the heliosphere should ebb and flow in time with the sun's 11-year cycle, but this did not fit any of them. The solar wind ebbs and flows over time, and when Voyager 2 arrived, the solar wind was at its strongest. If the predictions were accurate, the heliopause should have been farther out than 122 Australian dollars. Theorists' models of the interaction between the heliosphere and the interstellar environment are becoming more intricate now that the Voyagers are providing them with actual field data. According to the general image, our Sun left a hot, ionized zone and entered a patchy, partially ionized section of the galaxy. The hot zone probably developed as a result of a supernova. An ancient star nearby, or perhaps several, exploded at the end of their lives, heating the surrounding area and removing electrons from adjacent atoms in the process. One way to conceptualize the boundary enclosing that area is like a seaside, with all the water and waves whirling and mixing together. Magnetic fields twist and turn because we are in that sort of tumultuous area. Although the degree of turbulence observed can vary depending on the method of observation, it is not like the smooth magnetic fields that theorists typically prefer to draw. As a result of the heliosphere's influence on the interstellar medium, the Voyager data revealed numerous small-scale changes near the heliopause but negligible field variations on vast scales. It is anticipated that the spacecraft will eventually leave those turbulent zones behind and come into contact with a pure interstellar magnetic field. Saying goodbye to these innovative spacecraft won't be simple. Seeing things come to an end is difficult. There are currently 5 operational instruments aboard Voyager 2 and 4 on Voyager 1. They are all powered by a mechanism that transforms heat from plutonium radioactive disintegration into electricity, but NASA has been forced into triage mode as a result of the power output diminishing by roughly 4 watts annually. The Voyager's adventures will continue even when they are entirely silenced. Voyager 1 will pass Proxima Centauri, our closest neighboring star, in 16,700 years. Voyager 2 will follow 3,600 years later. After that, they will spend millions of years orbiting the galaxy, long after our Sun has disintegrated and the heliosphere has vanished, not to mention the pale blue. They will still be there, largely undamaged. They might be able to deliver a final message at some point during their journey, however, it won't be broadcast over the radio. If it is, it won't be by humans. 2 recordings, another form of antiquated technology, are used to convey the message, but they are not your typical plastic version. These are formed of copper, have a gold coating, and are enclosed in aluminum. Images and sounds intended to provide a feeling of the world the Voyagers came from are encoded in the grooves of the Golden Records, as they are known. There are 90 minutes of music, including Bach's Brandenburg Concerto No. 2 and Chuck Berry's Johnny B. Good, as well as images of children, dolphins, dancers, sunsets, and sounds of crickets, rain, and a mother kissing her child. Jimmy Carter, who was President of the United States at the time the Voyagers were launched, also left a message. "We cast this message into the cosmos," it reads in part. "We hope someday, having solved the problems we face, to join a community of galactic civilizations. This record represents our hope, determination, and goodwill in a vast and awesome universe." Thanks for watching another episode of Space Discovery. While you are still here, make sure to click the video on your screen for more mind-blowing videos about space.